we looked at purine degradation, and we had also looked at purine synthesis. Now, in this session, we'll be looking at pyrimidine biosynthesis. Welcome all, my name is Morris Munyeri, and I'm the Daktari. So, pyrimidine synthesis. Now, unlike the synthesis of purines, where we were constructing the purine ring on an existing ribose 5-phosphate. Here in pyrimidine, we first synthesize the ring, then we attach the ribose 5-phosphate, okay, which is contributed by phosphoriboside pyrophosphate, okay. Now, the sources of atoms in the pyrimidine ring are only three: glutamine, that is the amide group of glutamine, as you can see it here, the amide group of glutamine. Then we have carbon dioxide here. Then aspartate. Only those three. And like in the purines, where we had even the formyl groups. Okay. So only these three are needed to synthesize a pyrimidine ring. So the first reaction which we must carry out is, first we must synthesize carbamide phosphate. Okay. Now, this is the regulated step in mammalian cells, okay? But unlike in bacteria, the bacteria, you will see, I will show you where the step is usually regulated in bacteria. But in mammalian cells, it is regulated at this step, the synthesis of carbamide phosphate from glutamine. Please note this, let me take a pen. From glutamine and carbon dioxide. Okay, the glutamine is the one which will bring the amide group, the ammonia, and it is usually catalyzed by an enzyme known as carbamide phosphate. Please note synthetase 2. Remember, we had carbamide phosphate synthetase 1. I will show you the differences between the two of them in the next slide. Now, carbamide phosphate synthetase 2 is usually inhibited by UTP, okay? Also UDP will inhibit it, which is and UTP is the end product of the pyrimidine synthesis pathway. And also, it is activated by phosphoriboside pyrophosphate, okay? Please note that. Now, carbamide phosphate is also the one which is synthesized by carbamide phosphate synthetase 1, okay, is the one which is a precursor of urea. Remember the ornithine cycle, where we first synthesize carbamide phosphate from now ammonia and carbon dioxide. Then we form carbamide phosphate. Then we combine it with ornithine to form citrulline, a reaction catalyzed by ornithine transcarbamylase. That is in urea cycle or the ornithine cycle. But today we are looking at pyrimidine. Not that. If you have not seen that video, please go and see it now. Defects in this enzyme, the ornithine transcarbamylase, transcarbamylase will take your ornithine and add it to carbamide phosphate to form citrulline. Now, if you have defects in the ornithine transcarbamylase, as seen in this syndrome known as the Reis syndrome, you should have an apostrophe, Reis syndrome, this carbamide phosphate formed from now by the carbamide phosphate synthetase 1 in the urea cycle might usually go, instead of forming urea eventually, because you have defect in this enzyme, it will enter the pyrimidine synthesis pathway. Okay, hence it will cause increased availability of due to there will be increase in pyrimidines because the carbamide phosphate is in plenty. Okay, so this Reis syndrome usually develop in patients who have varicella, that is, or shingles, your herpes zoster, when you give them aspirin. So if one comes with chickenpox, varicella, or shingles, your herpes zoster, please don't give them aspirin because they will develop this Reis syndrome. Okay. Now, Now let's look at these differences. Let me take back my pointer. Now, carbamide phosphate synthesis 1, it is mitochondrial, unlike carbamide phosphate synthesis 2, which is cytosolic. Carbamide phosphate synthesis 1 is used in the urea cycle or the aniline cycle, but carbamide phosphate synthesis 2 in the pyrimidine synthesis. Now, which is a source of nitrogen in carbamide phosphate synthesis 1? Ammonia directly, but in carbamide phosphate synthesis 2, it is the amide group of glutamine, okay? Carbamide phosphate synthesis 1 is activated by the N-acetyl glutamate. Remember, how are we forming N-acetyl glutamate? We take glutamic acid, we acetylated with using acetyl-CoA, a reaction catalyzed by N-acetyl glutamate synthase, not a synthesis, synthase, and that N-acetyl synthase is activated by arginine. So if you have high levels of arginine in the liver, they usually activate N-acetyl glutamate synthase to synthesize N-acetyl glutamate, and the N-acetyl glutamate will activate carbamide phosphate synthesis 1, which will now form, which will catalyze, which will be used in the urea cycle. Now, carbamide phosphate synthesis 2 in the pyrimidine is activated by phosphoribosylphosphate pyrophosphate and inhibited by UTP and also UDP. Okay, please note that. Now let's look at orotic acid synthesis. Orotic acid synthesis. Now, here's where we are starting. We take 2 ATPs, carbon dioxide, and glutamine. A reaction, you can see here is glutamine, because now it is the amide group of glutamine which will bring the ammonia, okay? A reaction which is catalyzed by the carbamide phosphate synthesis 2, and this is the regulated step, okay? This is the regulated step in mammalian cells, and we will, from that we form carbamide phosphate, okay? Carbamide phosphate, here it is, carbamide phosphate, and we give out 2-ADP, an inorganic phosphate, and a glutamate, okay? Then after forming carbamide phosphate, we add aspartate to it, a reaction catalyzed by the aspartate transcarbamylase, and we remove this phosphate here, we remove that one, we add aspartate there, okay? And this step is the one which is now the regulated step or the committed step in bacteria, okay, like E. coli, this step. But in mammalian cells, I said is the first one. You can see from here, that is this part here, this whole part here is where aspartate was added. Remember, aspartate can come in either in aspartate or aspartic acid. So aspartic acid, if it is aspartic acid, here you have a hydrogen here, hydrogen. But here is, because we have aspartate, the hydrogen ion is in the medium, okay? Is in the medium where that reaction is taking place, is in the cytosol. So in the next reaction where we are carrying out cyclization, we cyclize this carbamide aspartate by this enzyme known as dihydroorotase. You can see water coming out. We usually take one hydrogen here, from here, and then this oxygen here, and that hydrogen ion which is in the medium, which originally originated from aspartic acid to form aspartate. Then that is what will form your water, and then after that we form this compound known as dihydroorotate. You can see here we remain with one hydrogen and here one oxygen there. Now dihydroorotate will move to the mitochondria, and this, the next step, this one which is catalyzed by the dihydroorotate, dehydrogenase, is the only step in pyrimidine biosynthesis which takes place in the mitochondria, because this enzyme is found in the inner mitochondrial membrane and it is FMN linked, okay? So we remove these two hydrogens. These ones are the ones which we are removed, okay? You can see they are removed. Then after removal, dihydroorotate becomes now orotate. You can see no hydrogens here. We have removed them. Now this is orotate. Orotate is the first pyrimidine to be synthesized. Okay. Then after this is already the pyrimidine ring. Now we need to add now the ribose 5 phosphate, and here we add it in form of the activated form of ribose 5 phosphate is phosphoriboside pyrophosphate. We add, then we a pyrophosphate is lost, and remember this pyrophosphate we will add water to it and form 2 inorganic phosphate. So this reaction is irreversible. Okay, this reaction is irreversible and it is catalyzed by the orotate phosphoribosyl transferase enzyme. Okay, orotate phosphoribosyl transferase enzyme to form orotidine 5' monophosphate. Okay, and see that is why it is added at the ribose 5 phosphate started at here, nitrogen at it is attached here. You'll have an N glycosidic bond here, and this nitrogen is at position number 1. Okay, attached to the carbon at also number 1. Okay, to form an N glycosidic linkage or bond. So this is orotidine 5 monophosphate. You can see 1 phosphate at position number 5. This is carbon number 1, 1 prime, sorry, 1 prime, 2 prime, 3 prime, 4 prime, 5 prime. So it is orotidine 5' monophosphate, OMP. Now, OMP is decarboxylated. We remove this, remove that. See, it is being removed to form uridine, form this uridine monophosphate, UMP. You can see. Now this is uridine monophosphate. This has several fates, and we will look at that. As I said, regulation of pyrimidine synthesis in mammalian cells. Now there is something which I forgot to tell you, is that carbamyl phosphate synthetase, aspartate transcarbamylase, and dihydroorotase. That is C for carbamyl phosphate synthetase, A for aspartate transcarbamylase, and D for dihydroorotase. They are these are the catalytic site of a single polypeptide. So we have a single polypeptide which has 3 catalytic sites. One catalytic site acts as is the carbamyl phosphate synthetase, and the other catalytic site, a different catalytic site, is aspartate transcarbamylase, and the other one is dihydroorotase, and that trifunctional polypeptide is found in the cytosol. Okay, so that is why this statement comes. Now, the carbamyl phosphate synthetase 2, it is a domain of a trifunctional CAD. That polypeptide is known as CAD. C for carbamyl phosphate synthetase 2, A for aspartate transcarbamylase, D for dihydroorotase. Okay, and it is inhibited by UTP, activated by PRPP. Okay, now in prokaryotic cells such as the one E. coli, aspartate, we regulate the pyrimidine synthesis at this level, as I said, aspartate transcarbamylase, and it is usually inhibited by CTP. Okay, CTP. Then we will also orotate phosphoribosyl transferase and OMP decarboxylase. They are components of a single polypeptide which is known as UMP synthetase. No, UMP synthase. Sorry, not synthetase, synthase. So they are UMP synthase is a bifunctional. It is a bifunctional polypeptide. Okay, it has 2 catalytic sites. Okay, that is why in defects of this, which we will look later, in orotic aciduria, you will find we have 1 orotic aciduria 1 and orotic aciduria 2. Okay, because you can either have a deficiency either in both or in one. Okay, Please note that. We will look at that now. What is the fate of the uridine monophosphate formed after decarboxylation of OMP? Now, it can be sequentially phosphorylated to form UDP and UTP. Note that UDP is a substrate for ribonucleotide reductase. Remember the other name of ribonucleotide reductase is ribonucleoside diphosphate reductase. And once we reduce it, we form deoxyuridine diphosphate. Now, deoxyuridine diphosphate is usually phosphorylated to deoxyuridine triphosphate, which is usually rapidly hydrolyzed to deoxyuridine monophosphate by the deoxyuridine triphosphatase. Okay, why should you hydrolyze DUTP to DUMP? So that we reduce the availability of DUTP as a substrate for DNA synthesis, which by doing so, we prevent the erroneous incorporation of uracil into DNA. So you don't want DUTP, you don't want DUTP to be incorporated into the DNA. So you have to hydrolyze it very fast to DUMP. Okay, and DUMP, I will show you what is the fate of DUMP. You have to hydrolyze it to DUMP and catalyzed by the DUTPase, the deoxyuridine triphosphatase. Okay, so that we prevent this from being incorporated into the DNA. Remember, uracil cannot be found in the DNA, only in the RNA. Now, how will you form cytidine triphosphate from now UTP? Now, cytidine triphosphate, CTP, is produced by amination. We just aminate or add an amine group to UTP, a reaction characterized by CTP synthetase because it uses an ATP with glutamine being the provider for the nitrogen, the amide group. Now, some of this CTP is dephosphorylated by nucleotidase to form CDP. So, which is a substrate of the ribonucleoside diphosphate reductase or the ribonucleotide reductase to form deoxycytidine diphosphate, which is then can be phosphorylated to form deoxycytidine triphosphate, which can go to DNA synthesis, or the deoxycytidine diphosphate can be dephosphorylated again to form deoxycytidine monophosphate, which can then be deaminated. We are carrying out the reverse of what we had done initially to now form deoxyuridine monophosphate. Okay, so you have seen there are two ways in which you can form deoxyuridine monophosphate, either from CTP or from either DCTP or from DUTP. Okay, so here you can see you have UTP, uridine triphosphate, you dephosphorylate it. Sorry, not you dephosphorylate it, you aminate it using glutamine. Okay, here you come out as glutamate, and you can see it is using ATP. ATP is being hydrolyzed, so it is a CTP synthetase to form cytidine triphosphate. And you have seen the two fates of cytidine triphosphate can be converted to CDP, then CDP to deoxy-CDP, then deoxy-CDP can be converted to either deoxy-CTP to go to DNA synthesis, or deoxy-CTP can be first dephosphorylated to deoxy-CMP, then deaminated to deoxy-UMP. Why are we forming these UMPs? Why are we forming these UMPs? Here we are. Now, deoxy-UMP is usually converted to deoxythymidine monophosphate, dTMP, a reaction catalyzed by thymidylate synthase. Okay, and it usually use N5, N10 methylene tetrahydrofolate as the source of the methyl group. I know you are asking yourself, why don't we use, if we just want to methylate UMP to form, sorry, if you want just to methylate DUMP to form dTMP, why don't we use just a S adenosine methionine? Why don't you use some or adomate? Because this is usually an unusual reaction. It is not the normal methylation, you know, because the tetrahydrofolate not only contributes the methyl group, the one carbon unit that is the methyl group, but also two hydrogen atoms from the pteridine ring. Remember, the folic acid, when forming folic acid, you used a pteridine ring and para-aminobenzoic acid. So hydrogen atoms from this pteridine ring are also used. So it is not only methylation, so you are carrying, it's like you are carrying out methylation and hydrogenation at the same time. Now, which will result in oxidation of tetrahydrofolate to dihydrofolate. Okay. Now, inhibitors of the mediate synthase, usually which are thymine analogs such as 5-fluorouracil, usually serve as anti-tumor agents. How? The 5-fluorouracil is metabolically converted to 5-fluorodeoxyuridine monophosphate. Is 5-fluorodeoxyuridine monophosphate, which becomes permanently bound to the inactivated immediate synthase. Okay. Hence, it usually makes the drug a suicide inhibitor. So when the immediate synthase goes to act on this 5-fluorodeoxyuridine monophosphate, the 5-fluorodeoxyuridine monophosphate remains bound to the enzyme. So it acts as a suicide inhibitor. So there will be no formation of dTMP. Also, dihydroxy DHF, which is your dihydroxyfolate, can be reduced to tetrahydrofolate by dihydrofolate reductase. Remember, conversion of DHF to DHF, dihydrofolate to tetrahydrofolate, is catalyzed by dihydrofolate reductase, and this enzyme is usually inhibited by folate analogs such as methotrexate. Okay. It usually decreases the supply of tetrahydrofolate, and by doing that, it will decrease the supply of tetrahydrofolate, and therefore, these drugs will not only inhibit purine synthesis. Remember, they not only inhibit purine synthesis. Remember, when we are looking at purine synthesis, we said we have two steps where we need formulation. Remember, the glycinamide ribonucleotide transformase reaction, we require a tetrahydrofolate, and also the 5-aminoimidazole 4-carboxyamide ribonucleotide transformase reaction, where we are converting ICA to FICA. You need tetrahydrofolate. So methotrexate will not only inhibit purine synthesis, but by preventing methylation of DUMP to dTMP, they also decrease the availability of this essential component of DNA. So they not only inhibit purine synthesis, but they can in a way inhibit also DNA synthesis, because for us we need thymidine in DNA, and they will inhibit. Okay, DNA synthesis is also is inhibited, and cell growth is usually slowed. Also, so those drugs, the methotrexate and 5-fluorouracil, are anti-cancer drugs. Also note that acyclovir, which is used in treatment of herpes simplex virus, is a purine analog. Okay, and usually inhibit the viral DNA polymerase. Okay, I want you to go and look at another drug which is also used in treatment of HIV, known as AZT. Let me go and look at that drug. So here we are, you can see deoxycytidine diphosphate diphosphate is dephosphorylated to form dCMP, which is then deaminated to form DUMP. Also, DUDP can be dephosphorylated to form DUMP. Then DUMP can be converted directly to dTMP. Here we are carrying out methylation, adding just a methyl group. A reaction catalyzed by the mediate synthase, which is inhibited by the 5-fluorouracil, and but the active ingredient, active this 5-fluorouracil is first converted to 5-fluorodeoxyuridine monophosphate, which now is the one which now acts as a suicide inhibitor of the mediate synthase. And in this reaction, remember, you need N5N10 methylene tetrahydrofolate, and we convert it to dihydrofolate. So, and we to convert this dihydrofolate to tetrahydrofolate, you require dihydroxyfolate, reductase. It can be inhibited by folate analog known as methotrexate. Okay. This tetrahydrofolate is usually converted back to N5N10 methylene tetrahydrofolate here. And this reaction, you require serine. I think you require serine and glycine. Okay. Maybe you should look at this reaction where you need to convert tetrahydrofolate to N5N10 methylene tetrahydrofolate. But you require serine, if I can remember, and glycine. Okay. Serine there and glycine. And we have an enzyme which is known as the, I think, serine hydroxymethyl transferase. Serine hydroxymethyl transferase. Sorry, I forgot to include that, but go and look in your textbooks. And I think that is the end of that. So we have looked at the pyrimidine biosynthesis, and maybe you should go back to that. Please remember this. Please remember this diagram. I urge you to remember it. And let's look at something to do with orotic aciduria. I said it can be caused by either deficiency of either of the two or both. Okay, and obviously the symptoms, it is usually caused by low activity of either or both domains of UMP synthase, which results in poor growth retardation. One will have megaloblastic anemia, and there will be excretion of large amounts of orotate in urine. Okay, how is it treated? You administer uridine, and also I think cytidine can be also used, and which improves the megaloblastic anemia. Okay, and also leads to decreased excretion of orotate. So please also remember that this is the only reaction which takes place in the mitochondria, because this enzyme is found in the inner mitochondria membrane. With that, we have come to the end, and thank you for your attention, and please subscribe for more anatomy and biochemistry content. Thank you.